So our first speaker is Nitin Bhat, did I pronounce it correctly? Who was a former PPL member and now works at CharmWorks. So, yeah.
Thank you, Juan. So as Juan mentioned, I'm Nitin Bhat and I'm a software engineer at CharmWorks. And today I'm going to be talking about recent communication optimizations in Charm++. So I'm going to talk about the existing Charm++ messaging API, and with an example, I will drive the motivation for why we needed a zero-copy API, and then discuss the two flavors of zero-copy API that we have, and then briefly mention the results, and then talk about a new experimental feature that we have added, which is another communication optimization for within node messaging. And then I'll finally summarize. So for those of you who know Charm++, this is very familiar. This is an example where I invoke an entry method where I pass a large array, in this case forces, and this is the CI file declaration, this is the .c definition, and this is how I call receive forces, where I'm passing forces and I'm passing the size of the array, which is in this case, I think 8 MB. So what really happens behind the scenes within the runtime? So these parameters are all at non-contiguous locations. So as soon as the call is made, a message is allocated with a header, and all these parameters are then copied on to that message, and this is what we call parameter marshalling. And then dependent on how large the message is, we use a particular networking protocol to send it. So as Professor Banda was mentioning, if it's a short message, we have similar schemes in Charm++. We use the eager protocol, and if it's a large message, we use the rendezvous protocol, which does RDMA reads. So in this case, since it's a fairly large message, we send the metadata over to another remote process, and using the metadata, the remote process performs an RGET, and then you get the entire message, and then we unmarshal the parameters, where smaller parameters are copied onto values and passed to the entry method, and larger buffers like forces, in this case, the pointer is passed to the entry method. So what we see in this case is there is copying on the sender side, where forces, being a really large array, is copied onto the message. And in case if the user wants the data within the within the entry method to be in the user's data structure, there is an additional copy which will have to happen on the receiver too. So potentially there are two copies, one at the sender side where parameters gets marshaled, and secondly, in this case I've not illustrated it, but it can be that forces needs to be copied into another array for the user to consume it later on. So these are the two copies that we are trying to avoid, and the motivation for having or needing a zero copy API is primarily that memory subsystems are what are causing bottlenecks in a lot of applications which are dealing with large messages, and we want to avoid that by using RDMA or CMA on enabled systems in order to slightly change the application logic a little bit and save on these copies and have advantages like reduced memory footprint and avoid larger allocations and avoid the copy. And also there are other benefits, like because we consume less memory, other page faults and data cache misses are also avoided. So the first zero copy entry method API that I'm going to talk about is something that I mentioned I think 2 years back in the Charm workshop. So I'm going to briefly go over it. So in this case, this is an API that is it's helpful to avoid the sender side copy but not the receiver side copy, and we call it an entry method API because it's a small modification in the entry method declaration and also change in the calling semantics in order to perform this. So what we do is we use the keyword no copy to identify that this is a large array and it has to be not parameter marshaled like regular arrays, and it has to be sent over using the entry method API. And at the call side, we also pass a callback to it. If we don't care about the callback, we don't have to, and we also pass it with this into this method called ck_send_buffer. And what really happens is, because now we are not parameter marshalling or creating a copy, the large buffer is asynchronously performed an rget on, and once the remote process gets the data, that's when the callback is invoked. And unlike the previous case where we could we could modify the data right away, in this particular case, we can only modify the data or free the pointer within the callback that we are passing. So in this case, quickly illustrating what happens, instead of the forces, there's the blue spot there is the metadata representing forces, and that's what is sent over to the remote process, and using the metadata, an rget is performed, and forces is obtained on the remote process, and then we unmarshal and do similar stuff. So what we did here was save on this particular copy, and once the forces is obtained, once this rget is completed, that's when a callback is called on the source process to tell the source process that, hey, you can modify the pointer now or free it if you want to. So that was a previous API which was kind of experimental, and also did not, it was kind of happening as if behind the scenes was, everything was happening behind the scenes. But in this case, we wanted to give one more API which allowed the user to perform more RDMA operations flexibly, and also provide more control over the API, and specifically for applications that have persistent messaging patterns. So I'm going to talk about all of that. So in this particular case, this is the direct API, which is a new API. Oh, okay.
No need to finish it in the time.
Oh, okay. So, so in the case of direct API, what really happens is we, instead of the runtime doing it behind the scenes, the user has more control, as I mentioned. So we have objects like ck_no_copy source and ck_no_copy destination, which represents source and destination buffer information. And the user, just like any other parameter, passes a ck_no_copy source, and that particular no_copy source is declared with the array and the size and also a mode. And don't worry about the mode, I'm going to talk about it, but in case if the mode is not specified, a default mode is used and the operation still works. And this particular no_copy source is passed to the entry method, and on receiving the entry method, receiving the no_copy source object, in the remote process, a destination object is created. Basically, it's like a pair that you want to make between a ck_no_copy destination and a ck_no_copy source, and this is the user buffer where the user intends to receive the data, and using that destination object, you say dest.rget, and then you pass the source object. In this particular case, an rget is performed, and that's how the user gets the data. So similarly, there is a very similar semantic that can be used for an rput, but in that case, you use a source object to perform an rput on a destination object.
You said this is for persistent.
Yes, this is the more persistent.
Then one time you may need to get that source,
Yeah.
and then on you can keep doing the rget
Yeah.
as many times as you
Yes,
want.
yes.
Different time steps.
Exactly, yes. So, yeah. So in this particular case, very similar to the previous case, but the user provides the no_copy source object, and that gets sent over to the remote node, and it's unmarshaled, and now the user here declares a ck_no_copy destination object, and then uses that source to perform an rget. And unlike the previous case where the forces was a runtime system buffer, in this particular case it directly comes and sits in the user buffer. And right now, since it's an asynchronous call, there are two callbacks invoked. One to indicate to the sender that the sending is complete. Essentially, not the sending is complete in the sense that the receiver has got the object, but it's more so that the receiver is in the process of getting the object, and the sender is free to free the pointer and modify the pointer. And the receiver gets a callback because just to know that the asynchronous get has completed and the receiver can operate on the data now. So there's a natural question that arises that which particular entry method, which particular direct zero copy API should one use? And I would say if you're a beginner user and you want to modify existing entry methods with large arrays, you can choose the zero copy entry method API, and you don't really care about receiver copies. But if you're a more advanced user and you want to control the operation yourself, in that case you can use the direct API. So as Eric was mentioning yesterday, there are different modes of operation which are like switches for how the whole API works and how the RDMA calls work. So the default mode is the unreg mode, where, and this is, before that let me just tell you that this is specifically relevant for networks that require memory registration. And out of the networks that we support, the only prominent ones that require memory registration are GNI, verbs, and OFI. PAMI, NetLRTS, and MPI don't require explicit memory registration from the user's end. So in this case, what exactly happens is the unreg mode is the one where the buffer is unregistered at the beginning and it's registered later on if it's absolutely required. For example, if there is a process which is within the same node, we use CMA to perform the remote read and we don't really use RDMA. In such cases, there is no registration required, so you can take advantage of unreg and save on the registration cost. Similarly, if the receiver is on the same process, because we are dealing with over decomposed objects, so it could be within the same process, in such case it's just a mem copy and you don't really need to do any CMA or RDMA related operation. The next mode is the CK buffer reg, which is registering it by default and this is done by the API, and this is the case where it does not differentiate between within PE, within physical node, and within the entire system. So all three cases are treated equally. And the next mode is the pre-reg mode, which can be used on the GNI and the verbs platforms, specifically because we have a pre-registered mempool, and the pre-reg mode allows you to allocate from this pre-registered mempool using CK-RDMA alloc and CK-RDMA free to free them, and that way you can save on the registration as well as the allocation because it's already pre-allocated and pre-registered. So all you're doing is getting chunks of pre-registered pinned memory. And then a no-reg mode, which is just for specifying the buffer information without dealing with any kind of registration at all. So I'm going to talk about results now, and I'm going to go through them pretty quick because we have quite a few networks that we have tried this on. So what we are comparing here is, as I mentioned previously, we use RDMA in the regular API too. It's just that in the regular API, we do the copy. But in the send API, we avoid the sender side copy, and in the direct API, we avoid both the sender and receiver side copy. So the results that follow are not actually comparing non-RDMA and RDMA case, it's more so comparing the processor and memory performance, because it's the case of comparing copy happening versus no copy happening on sending end, and in this case on sending and receiving end. So this is on BGQ Vesta, which is an ALCF machine, and with the PAMI interconnect, we see that with the in the first four columns, these four columns, I'm comparing the regular send API and the entry method, zero copy entry method send API, where there is no receiver copy that we are concerned about, and we get a speed up of up to 1.3x, and this is ping pong, and this is the one-way time for ping pong, and all these times are in microseconds. And the speed up in the case of the direct API over the send and receive API, where in this case I made an explicit copy from the provided pointer into one of the data structures, and in this case the RDMA call did it for me. So in this case I see performance gains of up to 1.6x. So this is entirely dependent not on PAMI interconnect as such, but more so on entirely on the CPU and the memory performance. And on InfiniBand interconnect, which is on this machine called Golub, I got performance up to 4.3x with the direct API, and with the entry method API of about 2.2x. So the difference why direct API is much better in this particular case, and this is all with the pre-reg mode, is in this particular case, since InfiniBand requires explicit registration, every time you make an entry method call, right now the system is naively trying to register even if it is previously registered. So, but in the direct API case, since it's a more persistent style of operation across iteration boundaries, pre-registered buffers are continue to be registered, and you don't really need to send the direct objects, the no copy objects again. Okay, so moving on CRAXE, we got performance gains of up to 8x, which was significant with the direct API, and on the Intel KNL cluster Stampede 2, we got with the direct API almost about 11x, 10x, 11x, and then so those were the results. And since we are running a little short on time, I'll move on to the next feature, which is another communication optimization, and this is using cross memory attach, or CMA, which Professor Panda was talking about this morning. So regular CHARM++ messaging within a physical host between two processes uses the network, and this has been happening ever since CHARM++ was developed, but we did have models of using shared memory transport within Node, but they were not as effective until now. So that's when we tried to explore using cross-memory attach, especially because it was a very simple API to use, and it is a part of the Linux kernel since Linux 3.2. And all we do in this particular case is we send a metadata message similar to the previous cases, and we send it using the network, and then we use the shared memory transport using CMA to read that that particular buffer from the remote process, which is on the same physical host, and then we send an ACK back to say that, hey, I've got the message, now you can free the source buffer. So using CMA, I again tested one-way ping pong, and this is across different machines. So in this particular case, we actually exercise the network, so we are comparing performance of the network with performance of CMA, which uses the processor and the memory system too. So on slower networks like Ethernet, we gained quite a lot from CMA, almost up to 4x. That's because the shared memory transport was easily beating the network. But on larger machines, which had dedicated supercomputing networks which were way faster, because we saw that after a particular threshold, the RDMA protocol was used, and since RDMA also has its advantages of bypassing the kernel and bypassing the network stack and not consuming CPU cycles, we found that a range of messages from a certain point up to a certain point is where CMA proves to be better, and it was lesser in terms of how beneficial it was. So we got performance gains of up to speed up of up to 1.5x. And on Stampede, since we use the OFI network, the performance gains were lesser, because I later realized that OFI within itself, using a PSM2 backend, uses shared memory transport for within node messaging. And then on bridges, the performance was similar, almost up to 1.13, 1.15x improvement. So we are still testing out CMA. It's disabled actually in the 6.9 release, but we have provided switches to enable it, and we are still working on defaults that would be good to have CMA excised in a particular range so that you can benefit from shared memory transport. So more results where MPI by internally also uses shared memory transport, so we did not see much gains on MPI platform as well. So concluding and summarizing my talk, we saw that the zero copy APIs were helpful in gaining performance over messaging because of avoiding the larger allocations and also avoiding the copies. In the case of direct API, you could avoid both the sender and the receiver side copy. And finally, we also saw that CMA is an alternative that we can try for inter-host, inter-process communication, and that way we can avoid the network. And for larger applications, since the pressure on the network is lesser because the SHM transport is taking care of it, we can probably see benefits of that as we are testing it further on. I can take questions now.
Can you make this automatic if I did move into an entry method? This is a feature request. So if I have some data and I know I no longer need it, and let's say it contains a std vector somewhere, right? Then you should be able to not copy the contiguous memory there. Say it's a vector of doubles. I would like to be able to say I std move it into the entry method. At that point, Charm++ should be able to detect this data cannot be used by the user anymore. They've literally given it up. I now own it. That then you guys keep it alive until it's been sent, and then maybe set something inside the pupper or something that keeps track of, I'm currently in a state where I'm allowed to take advantage of zero copy wherever I possibly can. And so then if you go through and you hit, let's say, a std vector, and you're like, I'm in my zero copy state, would it be possible to then just, sure, you can't inject it on the receiving end, but you can reduce a copy on the sender then?
Not avoiding the copy on the receiver end, but on the sender end. But if you... that happen automatically? I guess not. If you have a pointer to... I see, some
No,
copy
right,
by value
yeah.
thing.
Yeah.
So you need, the request is you can add an annotation, I was going to say CI file, in the CI file, wherever, that basically says for that parameter, I'm done with this, and you can free it, or not even free it necessarily, or you can free or just use it. Yeah.
C++ has this annotation. So in C++, if I pass in an R value reference, that'll make sense, then I basically have said, I am no longer taking ownership of this. I'm giving the ownership to you. And at that point, the callee knows that it is definitely guaranteed that it is undefined behavior if the person tries to use it after that. And so you guys can just hold on to that data until, and then you create maybe some internal callback or something that does it. But this would be really nice to have, and I think could be implemented so that STL types like std vector or something will automatically in those situations take advantage of it. And I think that would make to be something that most users don't need to see, and all of a sudden would just see their code be faster, I think.
Okay.
So.
Yeah, so I think that can be done. So we can work out the semantics and see how it goes. Yeah.